Hello everyone. So in my last video in this uh, WSDM Cup competition in Kaggle, I did some idea over the tokens, the prompt lengths, and the character distributions and the model frequency maps. I plotted all of them, and we did some standard EDA stuff. So today we will be majorly focusing on training LLM on this data set so that we can classify them, like which one is better, and that's the motto of this competition, right? So let's start with creating dependencies, like installing all the dependency that we will be needing for training. So I need pip install so Kaggle already has transformer, but we will be needing the latest version of transformer to use Peft training, like that parameter efficient training, where we will be using LORA. Then we will also need Peft. We will need accelerate. Then we will be needing bits and bytes. Yeah. So let's save this. Um, I have this. Now I need to start the session. So yeah, so first we will be coding everything. Then I will explain you all the sections that we will be coding. Okay. So session is starting, and before that I can do some imports. Importing modules. Okay. Uh, yeah. So we have this. We will be needing GPU. So once we finish this, then uh, we will configure the kernel to GPU. There are two types of GPU, I guess. We can configure it to this one because we don't need two separate GPUs. So we will need only one GPU. So need LoRa config, then get Peft, then prepare, I guess, model for K-bit training. Yeah, so we will be needing this. Then next thing we will be needing is yeah, so we need to split the data set. So from sklearn, uh, just a second. Yeah, okay, we are back. So yeah, we'll be needing metrics. So as in the competition, accuracy is kind of a metric. So we'll be needing log loss and accuracy. Log loss we will be using while we are training our model. So then we will be needing sklearn, model selection. We can go for a 5-fold training. Strati, yeah, 5K-fold. Yeah. Then yeah, to read the data sets, we will be needing pandas. Then using warnings and to oh yeah, so to ignore the warnings, I will simply say ignore. Other things we'll be needing, yeah, data set, so that we can convert the data sets. What else? What else? Yeah, so in this video, I'll be training Gemma. So those of you who are not aware of Gemma, Gemma is a LM which was launched by Google. So it's open source, not open source, but we can easily use it from Hugging Face. So Gemma Hugging Face. So yeah. We have different versions of Gemma. There is a 7 billion, 9 billion, there's a 27, and later on we have a very big model. So yeah, here we will be using a 9 billion model, but we will not be exactly using the 9 billion model. We'll be using a quantized version of that. Okay. So yeah, so we got the Gemma for classification class. Then we got Gemma tokenizer. So we'll be tokenizing our prompts, our sentences, and we'll be using this to initialize a classification model for Gemma. We have this. Then the next, oh, yeah. So yeah, then the next thing we'll be needing is we'll be needing a trainer. Okay, and this is from Hugging Face, and it's pretty cool and very simple library to use if you want to train LLMs. So yeah, then you have a trainer, and we have to pass this training arguments, and this will be consumed in the trainer when we will initialize it. Then we need a data collector. So this is something like a preprocessor. So this will take care of collecting all the data and sending to the model batch wise, and also while sending it, it will pre-process that batch. And here the pre-processing step will be tokenizing the text corpus. So yeah, we have all this. Anything else we'll be needing? Yeah. So let's start off. One more thing. Have we? Yeah, we need to run this first. So let's select our GPUs. We'll be saving it later. Save files only. And yeah, um, yeah, and it should restart, right? Um, After that, we'll be creating some config so that we can use that while uh, making the training. The session is starting, it's loading. Okay, I need to install this. Run. Okay, it's installing, and it will again say me to restart it. Okay, for that I can complete this. So let's keep it max time. So we'll be using Gemma, and we have to provide like how much context length we have to consider for training. Okay, then another argument we'll be needing is per device batch size, and let's complete this batch size, and that to be 2. Then per device eval batch size, that so training will require for training we need lesser batch size because back propagation will be happening. For evaluation we can increase it to 4. Then let's set the gradient accumulation step to this, and number of epochs I'll be doing for 1. You guys are like feel free to increase it to 2 or 3 based on your endurance because I say endurance because this will take a long time even for 1 epoch. So that's why we are also using gradient accumulation steps. So yeah, then since we will be using LoRa, we will not be we can fine tune on all the layers, but let's keep a config so that we can select the initial like how many number of initial layers we'll be using for fine tuning. So let's call it freeze layers count, and let's keep it to some like let's say 10 maybe. Okay, then we'll be using learning rate, and let's keep it to 3 5. Then we will be needing some warm-up steps. Let's keep it standard like 20. Then yeah, so let's put LoRa parameters here. um, so LoRa params in in their paper they have mentioned you can use between 8 to 25 any value. So let's use 8. Okay, then LORA scaling factor, which is LORA alpha, and in the paper they used like 1:2 ratio. So if you are using 16, we can put alpha as 2, and this is like how much I will restart it once I complete it. Yeah, so how much scaling you need to put on the weights. Okay, so it scale those weights, it's multiply. So the scaling parameter will be like LORA alpha upon LORA R, and that amount will get updated in the weights. So yeah, we will discuss on that once I finish this coding. So we need to keep some dropout, and let's keep it to 582. Then I don't want to put any bias. uh, Keep it none. Then the most important thing, seed. I will need seeds. Yeah, so uh, this is everything. One more thing I'll be missing. So yeah, we are training it. So these are data params. Yes, and these are training params. Let's see what all things we have. Gradient accumulation and epochs, pop steps. Uh, yeah, we need an optimizer. So I can say optimizer. So we will be performing some quantized training. So we'll be using Adam W8-bit. So yeah, so data params, training params, you have LoRa params. What else? What else? What else? What else I need? Yeah, like I said, we'll be needing a quantized version of Gemma 9 billion model. Okay, so there's a very famous author, Unsloth, and this community is being very indulged in building quantized versions of LLMs. Let me check whether this is running. Yeah. So, and luckily in Kaggle we also have this. Okay. So I can simply import this. So let's call add import, and let's call wisdom d cup. Then in the discussion, this same guy has uploaded the Gemma 9 billion model. Okay, I need to put. Am I getting anything? There should be an sloth version. Yeah, let's put. We need Gemma 2 9 billion. I'm not finding anything. Okay, 4. Hmm. I need this one. Let's search in Kaggle itself. So Gemma. Yeah, this is the one. Okay, and how do I get this? I will just copy this. Yeah. Wait, transformer, and yeah, I want to add this. Yeah. So yeah, this is something we can use during inference. Okay, but right now we are training it, so we don't need it actually. So we'll simply copy this thing. I have to find out the name actually. So it should be something Onslaught. Yeah, I already have this, right? So something 4-bit. Yeah, this is the one. So let's copy this ID and let's call it model Onslaught. So yeah, I guess we are good at config. Now let's load our dataset. Okay. So as we have seen, these are Parquet files. So let's call df and let's perform read Parquet and let's directly get this name. Yeah, so we have this and let's look at the dataset once. Okay, let's first restart it. Yeah. Now we should be able to do this. It's loading. I'll just check the name once. What have I written? Gemma 2 for classification. Oh yeah, Gemma 2 for sequence classification. Yeah, that's a full name. And yeah, so we also need to import the task type also so that we can tell the LORA, hey, you need to do classification. This should work. Cool, this worked. This should work. Let's close our console. Cool. So we have up to data sets. We have, so now let's look at our data set. Yeah, so we have this and we need to modify our winner thing. So I will simply call int. So wherever that I have model A, I will simply call it 0. And wherever I have model B, I will call it 1. So let's look at a sample of 10 rows. So yeah, I got zeros and 1. So wherever I have model B, I got 1. Wherever I have model A, that I am representing with model 0. Cool. Now let's split our dataset. Into uh, into folds. Okay, so escape splitter. So rectify k fold. Okay, now can perform some splits here. Have I given any splits? No, right? Okay. So let's split for 5. Okay, and shuffle. So we are doing stratified k-fold because the languages of prompt are different, right? So we cannot like simply, so this also I have discussed in my other video when I was doing the Jane Street video, why stratified k-fold, why people often do stratified k-fold. So the main idea is like here languages that we have here, right? So we do not have a very so there is some skewness in the language. So majority of the content are English, as you can see. This was the image, I guess. Yeah, majority of them are English, whereas in the minorities we have few languages and their frequencies are two only. So yeah, so in order to uh, like divide our train and test set properly, so that we will have equal number of samples from each bucket, and from bucket here I mean language, we perform this stratified k-fold. So we have this now. To maintain the reproducibility, we will set the C to whatever we have mentioned in stratified k-fold, that's 42. Okay, now we will simply split this. So for IDX, I need val index. Enumerate. Now let's get splitter. I want to split DF and on the basis of my winner. Okay. Now data set. Yeah. So there I have told you we will be using for language. Now for quickly uh, running the training, I'm simply doing it for winner, but it's uh, better to do it for languages. So you will have proper splits. Uh, okay, we got this. Now let's look at our DF now. Uh, yeah, we got DF. Yeah, so we got the splits. Nice. Okay. Actually, let's do it for language only. Yeah. Okay. So with respect to language, we got everything. Okay. Um, cool. This is set. Now we'll be needing we'll need to split our train and val set. Okay. So oh yeah, we cannot do this. I need to split it with respect to our labels, right? Yeah, yeah. So we don't run this. Yeah. Uh, So yeah, we cannot do it with respect to language now because I have to split it here. Now I will not be doing a five-fold training here because that will take a very long time. I will simply run for one of the split, okay, so that we can quickly run one training instance at least. So wherever, let's take the 0th one, okay. Equal to 0. Now I can look at my train df shape, val df shape, and let's put them in a print. Okay, now again also print out train df my winner value counts, and also let's, yeah, Also, let's print value winner dot value counts. Okay, cool. So we have a very equal distribution, so we should be good to train the models. Okay, cool. Now we have to convert our pandas data frames into a data set so that the trainer that we will be using for training our LLM, it can consume it. So it's pretty simple. So just a second. I got it. Yeah, sorry about that. Cool. So we got the data frames, so we need to convert them into data set so that our trainer can consume it. So we'll be converting our data frames into data sets. So we call DS. We'll be using the data set, and we can use the pandas method, and we will provide here our DF. And similarly, we will call it for our validation data set. Cool. Yeah, we should do. Okay, now let's load up our model and tokenizer. Okay, so let's initialize our tokenizer. So we'll be calling Gemma tokenizer fast, and I'll be calling it retrend, and I'll be using config model. So this will download my tokenizer, and I'll provide the end of sequence token to be there, and my tokenizer of padding side to be right. Okay, now once I have this, uh, it's better to put everything in a class, I guess. In a function also. So yeah, both of them works. Okay, so this will load up our tokenizer. Then we need to load up this thing, right? So yeah, so we can create a function actually, but let's make it productionized. So let's call it Gemma tokenizer self. Okay, now this, so my config is already set. Okay, so I'll just call this, and here I will call this. Okay, this, make this tokenizer here, then I'll call this, and we can initialize our max length to be whatever max length we have. Okay, now we can define a call method so that we can use this class as a function, like the object as a function. So I'll be needing a prompt. Okay, so the prompt, and as per Gemma standards, so they use these delimiters, these kind of delimiters. Okay. Let's put them in a f string. So I got this prompt. I will put the text here. Okay, and I'll be calling it for text in so we'll be getting some batches here. Okay, so for text in batch, and this batch is nothing, like as I told you. So we will be calling out data collator, and this will be running this tokenizer there. So it will produce some batches, and it will perform the pre-processing there. And here our pre-processing is the tokenizer. Okay. So we have prompt here. So yeah, that's the name. So prompt. Okay. Now we will be loading our responses. Okay. And this we can load it with again f string. Okay. So we'll be calling response A, we'll be calling this, and we can add some prompt here. But I don't want to do that because since we have multiple languages, if I simply wrote English here, so it will make the model confused, like, hey, you have two different languages and you are telling me to classify them, which one is better. So it can spawn some random or some noise towards the model. So let the model uh, learn over multiple languages. Okay, so that we will not ruin mixing up of languages in the prompt. Okay, so we'll put a response aid delimiter here, and we will pass the text here. So text in batch of response A. That's the that's the thing. Then we'll be needing this here. Response where response. So you convert it to B. Then we will be sending a tokenizer with the labels. Okay, so we got the batch. Now we'll be returning a dict. Okay, where we'll be returning the labels. Okay, and this here we will, so here winner is our label. Okay, so we'll be returning this, and here we will be uh, returning the concatenation version of all this, and like this prompt, the response A and response B, and we will be putting a tokenizer, running a tokenizer over them, and we will be putting that here. So I can simply write something like okay, so the tokenizer all gives me a dict kind of thing, which I can transform into a cogs. Okay, now here I need to concatenate all of them. So the idea will be creating another tuple. Okay, and here I can put the, so every tokenizer has default argument. This is the max length, and here I will simply initialize it the max. Cool. So we have this. Now we will not be using the full context for Gemma because we do not have that much resources. We only have around 29 gigs of GPU memory. So it might happen we might hit the limit. So we will be using 2048 length, and a couple of text we observe here, they are like more than that, like they are, so the number of tokens we may get from those texts are more than 2048. So if you see here, we have this kind of a distribution. So if I use 2048, we will be somewhere here. Okay, so it will help us in training the model faster, and it will also prevent us from hitting any OOM errors, like out of memory errors. But yeah, we may lose out on accuracy. Okay, because we will be uh, truncating a couple of parts of the original text. So yeah, but since this is in Kaggle and not a machine, so we have to cooperate with whatever we have, right? So yeah, so we have this. Now let's write this. We have prompt here, and we will have response A here, and we will have response B here, and that will be for prompt. Let's destructure it. In Python we call it unpacking, right? Yeah. So zip of whatever prompt we created, response A we created, and response B we created. Cool. This, it has this, and we are missing a comma, and we have this thing. Yeah. Equals this. Yeah, we should be good to go. I guess it will not work if I add cogs here. So I can use it something like this. Cool. So we'll be returning this. Okay. Now let's quickly check this out. Okay. So let's call it encoder, and we will call our tokenizer here, and it doesn't take anything. Then let's convert our train ds here. So we will call train ds, and we will call a map over this train ds with our encoder, and we will set the batch argument as true. So this will return us a couple of batches. I mean, it will convert everything into batch. We have valds, we are batching. Let's run this. Yeah, we downloaded the tokenizer, and yeah, we got an error, and this error is for let's look at batch here. So this is how the batch looks like. Okay. Yeah, so okay, can I use this? Text input must be of type string, list of strings, or list of strings. So what am I even giving you? I'm getting prompt, I'm getting response. I'm getting prompt, I'm getting response, I'm getting response B. I think this syntax is not correct. But Okay. What's the issue? What's the issue? I got this right. Why are you breaking? It's because I'm not putting them into list. Okay, I think it doesn't take a tuple. Yes, okay. Yeah, so I accidentally clicked my panic button and I just closed the tab. Not sure whether everything is loaded. Oh, okay, somehow my session is there, which is nice. Okay, yeah, where are we? We were here, right? So let's put it here. Okay. Call this. Oh yeah. Oh, it should run. Yeah, it ran. Cool, nice. So we can see it is tokenizing our thing, and yeah. Now let's this is for our tokenizer. Now let's load the model. Okay. Now we'll be using Gemma 2 for sequence classification. So from pre-trained. Okay. We'll be using the model name as whatever we have taken from the Hugging Face. And then we'll say how many labels we have. We have two labels. One is model A, model B. Okay. Then we need somewhere to tell the torch D type will be using the data types. And yeah, so for that I also need to import torch. Cool. Yeah. So we have to organize everything. Now, if you want to look at this, it will look something like this. Okay. So the trainer can consume this. Okay. Uh, but yeah. So the trainer will be using these things what we have mentioned. So it will not use any other stuff. Yeah. And you can see we have loaded around 38k, around 39k rows. So yeah. So have this. Okay. Now we can say torch. We'll be using float 16 so that we can save up on competition. Okay. Then I will simply say device map to auto so that if ever I accidentally selected a CPU kernel, like a non-GPU kernel, I can still run my code. Yeah. So it will automatically checks if we have GPU. So it will automatically take GPU as a config, and it will run the training in GPU. Okay, so I will run this. So this will download the model from Hugging Face to my Kaggle kernel. Okay, now since we will be training this model, I want to disable cache. So cache is something we use while inferencing from the model. If we are giving the same prompt to the model, this cache uh, will uh, send back the response that the model gave, so that we will save up on computation. But since we are training here, we should disable the cache. Then we need to prepare our model for a k-bit training. Okay, so this utility will convert our model like a scaffold. Okay, so people who are not aware of scaffold, so scaffold is something we use like we use it everywhere. So it's like a whole, some kind of a placeholder. You put some stuffs there. Okay, so here our stuff will be the LORA weights, like the weight matrices that we will be adding to the model. Okay, so we can look at how the LORA thing works. Okay, or yeah, something like this. So here we will have our model layers. Okay, and with each layer we will be adding some two matrices. Okay, and these two matrices will be updated in our training. So in order to add these matrices to our model, we need some kind of a scaffold over the layers, so that we can add these matrices there. Okay, alongside the model layers. So for that we will be needing this prepare model for k-bit training. Cool. Now once we have this, we have to load our model with get Peft model, and we will be providing a LORA config. Okay, so let's call it preparing model for Peft. Okay, now we'll be creating a LORA config. Okay, um, creating a LORA config. Okay, now config. So we have already loaded this LORA config from Peft. Here it takes a rank. Okay, now rank we can pull it from our config. So that's the LORA parameter. Actually, we can copy all this so that we can use them directly here. Okay, LORA I gave this thing. Okay, it doesn't look like that. Yeah, let's. Yeah. Okay, we don't need you. We don't need you. We don't need you. I need a comma here. I need a comma here. I need a comma here. Cool. We got up to this. So we have set the initial configs that will be required for training. Then we need to tell LORA at which layers we want to put this matrices. Okay, and in order to tell it, we need to provide two things. So one is what is our target module. Okay, so you guys hold a background in Torch. So there we called layers as modules. So that's why the name is target models. So we will be majorly focusing on this the attention layer. So we will be marking our queue, like query key, and our value matrices. Those things we will be updating. So I will just write that down. Okay, now we are training Gemma 2 model. Okay, so if we look at Gemma 2, okay, or let's say how many layers are there in Gemma 2? Okay, there's one Keras thing. Yeah, so Gemma 2 has around so Gemma 2 9 billion model. Okay, so it has around 42 layers. Okay, now a good approach will be to add all this LoRa weights to the 42 layers. Okay, and then train the model. But again, I don't want the GPU to crash. Okay, if we are doing those kind of thing, we might need to lower down our batch size. Okay, so in order to avoid all that, okay, uh, I will set it. I will just freeze down some, not all of the 42 layers. Okay, I will be using some initial 10 layers. Okay, that's why when I set the config, I put a 10 there. Okay, so if you recall this thing, freeze layers count. Okay, so here we will be locking down the initial 10 layers that Gemma has. Okay. So we'll be calling our uh, layers to transform parameter to, so it takes the index of those layers. Okay, so I'll be freezing the first 10 initial layers. Okay, or otherwise, to save up again on computation, I can increase it to, let's say, 15. Okay, so I will say I for I in range, I know 42 is the number of layers that Gemma has. Okay, and I will put I only if I is more than my these layers count. Okay, cool. So after uh 15, we will be putting the LoRa weights to 16 to the 42nd layers. Okay, I'm telling in the one base indexing. So you have layers transform here, you have target models here, and one more thing we should add is the task type. Okay, this will tell the Peft model, hey, you are training this model for a classification task or for irrigation task. Okay, so I'll say task type as sequence classification. So this is the syntax for that. Okay, let's check this out. Oh yeah, I haven't put LoRa there. Yeah. So I gave the rank, I gave the alpha, I gave dropout, I gave bias, I gave target, and um, I gave the number layers I want to do. So yeah, cool. Now let's run this. Prepare model. Prepare model for Kbit training. Cool. So it got loaded. Now, if you look at our model, this will give you a torch kind of a thing. So here you can see we have some LoRa layers here. Okay, but in the initial 0 to 14, 0 to 14 in one base indexing will be like 1 to 15, right? So we do not have any LoRa thing here, LoRa weights here, but here if you see we have a LoRa linear 4-bit matrices that we have added. Okay, so yeah, cool. This is there. Then the major thing is to uh, so that, okay, so now let's build our trainer. Okay, okay, now before trainer we should also create one function that will capture our metrics, like our matrices. by metrics, I mean the losses and the accuracy that we are making in the training process. So for that, we need a function to do that. Okay. So we can call this as metrics. Simply, I'm coding at metrics. Now I can call some fancy name, get my metrics, and this will call the evaluation. Okay. Now here I will say whatever preds I have done, predictions. Okay. And take the labels from my prediction. Okay. Now take the probability from the prediction. Now this will be in torch. Okay. Now first load them in numpy. Now let's convert them into float, put as softmax over all the values. -1, like it will simply, so you will have a list of probabilities. So softmax will run over all the lists, the nested list. Okay. And then I will call numpy again over it. Okay. So this will be a numpy array. So I will convert into a torch. I will convert it into a floating data type. I will run the softmax over the nested floating values. So this will look something like this. Okay, you will have some probability like this, something like this. Yeah. So the softmax -1 will take care of running on these things. So yeah, and then we will convert into a numpy. Cool. None. We will compute the loss. So we have imported as log loss from sklearn, so we'll be using that. So we can call our y_true as the labels and y_preds as the props that we are getting after softmax. Now we will call accuracy score y_true as my labels, y_preds as my props. Okay. And here I need to give -1. I need the indices. I don't need the probabilities. For computing the loss function, I need probabilities. Then I can return it in this way. So accuracy. Here I'm up. Yeah, every time I'm using that. Then loss. Okay. So this is the function. Now, first let's create our training arguments. Okay. So so let's initialize our trainer. Okay. So here we will be using our training arguments. Okay. Now here we'll be writing bunch of stuff, and here we'll be providing our model here, our tokenizers here, then train dataset as our train DS. That's the thing that we created here. Yeah, that's train DS there, and we will be giving val dataset as our val DS that we have created. Cool. Now it also takes this compute metrics method where you give your monitoring method, and this will run. So it will push a evaluation log, and then all these things will be computed, and we will get the tick. Okay. And other thing, we will be needing a data collator with padding. Okay. Cool. Now let's build our training argument. So what all things we'll be needing? So first of all, I need a output directory. Okay. Right now I can directly save it here. That will be one model instance. So first thing we need to do is where we want to save this. Okay, so here I can simply say Gemma to classification, and um, we have done pipe splits. What else we have done? Okay, so let's put 2048 at sequence. So let's call seclen as 2048. Okay, now we have this output directory here. Now we want our model weights. So if we are getting any improvements over the model, then we should override it. Okay. Let's set it to true. So these are some standard. I'm forgetting the syntaxes. Training arguments. I think this. Yeah. Yeah. So we have all this bunch of stuff. I just need few of them. Um. Step. Step. Okay. Let's. So number of training epochs. Okay, now this is something we have already defined. Batch size. Yeah, so train and val batch size, and let's take eval. Okay, cool. Then I need to put gradient accumulation steps. Gradient accumulation steps. Then our eval strategy, we can set it to default, I guess. Where is that eval there? Yeah. Yeah, so we need the evaluation to be done at the end of the epoch, so we'll mention epochs there. Epoch. Okay, now save strategy. Now we will be saving the model weights with respect to number of steps that we have covered in the epoch. So here our strategy will be steps. Okay, now save steps will be 10. Save total limit, let's say 1, then fp16 to reduce the computation, then optimizer. I'm not sure about this parameter, just bunch of configs. Yeah, optim. So config optimizer, then we put learning rate, and let's call learning rate here. Then we have our warm steps also, warm up steps. And what else we need? Okay, like this. If I want to run it in the background, I can uh, create a logger also. Okay, so logging steps, let's call it 5. Okay, and yeah, I think it's good to go. Then cool. This should be our output directory. This is one. I will just verify the configs that we have created. Okay, folks. Yeah, that's it. That's a max length optimizer. Yeah, optimizer steps. LR. Okay, we have taken this as LR. And yeah, LR. We have tokenizer, train DS, val DS, and yeah. Okay, so we have created. Okay, so epochs. Where is epochs? An epochs. We have created as an epochs. I think that's eval. Yeah, as per the name. Tokenizer encoder. And encoder. Cool. This should load our trainer. Now we have the final thing to do, and it's kind of the most difficult step. We have to run this method, and this will take care of all the forward propagation, back propagation, updating our weights, and also showing up the logs, all those things. Now let's run this. Yeah, the runname is currently set to the same value as training output directory. If this was not intended, we specify a different runname by setting training arguments not runname. Cool. Um, cool. Now this should consume my GPU, and I should see my GPU being red. I'm just waiting for that moment. But yeah. Start the training. Okay, so while this thing is training, uh, we can look at some other aspects. Why is it not showing? Mhm. Okay, this should begin the training. So let's start from the top. Okay, so we initialize our environment, we loaded all these modules, then we set some configs here. Okay, now while training this large language model, so usually what happens is we do not train them as we typically do for a neural network. Okay, so we usually perform some kind of some parameter efficient kind of a training. Okay, now what that basically means is, so you will have some your model layers here. Okay, let's call it your LLM layers. Okay, now usually if you think of this fine-tuning approach, so we will take a data set, we will train our model on this LLM, and all the layers will get updated. Okay, now updating all the layers and training all of them requires very high GPU resources. Okay, so instead what we do is we do a Peft kind of training. Okay, the idea is these layers are already trained on massive amount of data sets, so lots of pre-training has already happened over these LLM layers. Now to narrow down their generation capability on a specific task, we just need to fine tune the model a little bit. We do not want to override the whole layers again based on our new data set. Okay, now one way to achieve it is adding some small like matrices, okay, against each layer. Okay, now these layers are not so these layer will get updated during our Peft training. Okay, so we call it parameter efficient fine tuning. Okay, now the major drawback of a normal fine tuning is that whenever we are fine tuning an entire network, it sometimes forgets about all the things that he has learned from pre-training, and with the new data set it's just focused on the new data set. Okay, but during LLM training we do not want those things to happen. Okay, so we are only interested in small updates in our fine tuning. So we usually use this kind of approach, we call it Peft. Okay, so here we introduce some sidecar kind of layers. Okay, now these layers have the same dimension as of the training layer. Okay, now one might ask, okay, if they have the same dimension, then how, so it will be same as like training all these layers, right? And this will be again very intensive. Okay, now what these guys have done is, so you have this your uh, let's say pep layer here. Okay, we know in our high school math that we can decompose a matrix into two matrices. So for example, if we have a 4 by 4 matrix, okay, now in order to obtain a 4 by 4 matrix, we can take a row matrix, okay, and multiply that with a column matrix. Okay, so let's say this is A, B, this is 1 and 2. When we multiply this, we will get A1, A2, and we'll get B1, B2. Okay, so from here, so from a 2 cross 1 matrix and a 1 cross 2 matrix, we got a 2x2 matrix, right? So here the R that we are giving, okay, the rank of the matrix, okay. So the LORA R parameter that we have set, that basically decides the rank of these matrices, okay. So here we are not updating these kind of matrices, we are updating these kind of low dimensional matrices, okay. Now once this matrices gets updated, we multiply them, we get this matrices, and then we add them up to our original transformer layer, okay, and then we get a new layer, okay. Now why it is efficient? So from this matrix decomposition, we are breaking this whole matrix into two smaller matrices, and if you look at the number of values you have here, that basically uh, is determined by the rank of the matrix that you are given. So yeah, that's why the rank of the matrix is somewhat a hyperparameter. This is not something the model learned during the training process. We give a hyperparameter like this, and with that it increases the number of rows and the number of columns. So yeah, now another hyperparameter we talked about is the um, LORA alpha. Yeah, now this is something, so whatever uh, weights we have here, like a1, a2, b1, b2, okay, this is something which act as a scalar, okay. How much we want the weights of this two thing, like all the values of the matrix, okay, to update, okay. Now this is defined by our LORA alpha. Okay, the handwriting is not that good. LORA alpha upon your rank, okay. Now you can clearly see, as we go on increasing our rank, the scaling quantity will increase. So whatever weights we have, those will get updated to our scalar times the, like the new weights will get updated with this scalar times the old weights, okay. That's called new. So yeah, this is essential because if we increase alpha to any arbitrary value, it might happen all of our weights are kind of overshooting, so we may be losing out the proper fitting for the model. So yeah, these two parameters are pretty much essential for us. And yeah, like we spoke, so in order to prepare your model for quantized training, you need to put your model inside a scaffold where all these layers will get added over the model, and then you perform the fine tuning, okay. So that's why we use that prepare model for k-bit training, all those stuff. So yeah, I'm pretty curious why this is not running. uh did I mess up anywhere? Okay, so we have all this thing now. Yeah, now training transformers, it's pretty expensive and time consuming process, right? Because we have so many layers and so many updates will be happening, and we will be training all the transformer over a big amount of data set, right? Now usually what we are interested in, so when we have very large networks, so even like small lengthy updates will worth for updating the weights, okay. And okay, what does that mean? So in a typical epoch, we have some training steps that we have that we give, right? So how many steps we need for every epoch, okay. So now in those steps we'll be supplying batches to the model for training. So when we have massive amount of data set, we can actually update the model weights during the steps. Okay, so in a typical neural net, like a neural network kind of a fine tuning process, or even in a training process, we wait for all the epochs. Okay, say epoch 3, 2, 1. So we go by epoch, and in each epoch we provide all the um, batches, and after that we perform weight updates. Okay, let's say weight updates. Okay, but when we are dealing with LLMs kind of model, we are dealing with large amount of data set. So doing this process will not be efficient. The reason being, since you'll be giving lots of data set, so there will be many varieties of the data set. Okay, so at the end of the day, so the gradients that you are calculating at the end of the epoch, they might not be a good representation of all the variety of data set that the LLM has saw. Okay, so in order to accommodate that, we break down the epochs into multiple steps, and in each step we update the weights. Okay, so let's say step 1, let's say the step length that we are mentioning, some 10, let's say. So at step 10 we will update the weights. Okay, at step 20 we will update the weights. At step 30 we will again update the weights, so that we will not have to wait until the end of all the epochs and then the updation process to happen. Okay, we can do it intermediate. Okay, so that's why we put this gradient accumulation steps. Now here I have mentioned 2, which means like at every 2 steps we will be updating the weights. So yeah, then what else we have? Then we have this cute little warm-up steps, and this is nothing. So this is some kind of a uh, you can say cherry on top of training. So usually what do we say? So whenever we are doing any neural network training, so we want our learning rate to be high. So if I draw epoch versus learning rate kind of chart, so as our epoch increases, we want our learning rate to decrease. Okay, so that we will not perform large updates over the weights. Okay, so the assumption being, as our epoch increases, the weights will get the weights will get stabilized. Okay, so as the weights are stabilizing, we do not want the updates to happen on a larger scale. So that's why the controller parameter, which is the learning rate, we want that also to decrease. Okay, now this is the typical neural network training, but it might happen in order to reach this stage. Okay, so this is some kind of a ideal stage. Okay, where your weights are also going in a good direction, like the updation is also going in a good direction, and as your epochs are increasing, and that's why you are decreasing your learning rate. Okay, but it may happen that in order to get to this ideal stage, okay, which is at here, you have to do some kind of random updates for the weights to happen. Okay, so that you will get into this stage. Okay, now this is where warm-up steps comes in. Okay, uh, warm-up steps. Okay, so during the warm-up steps that we have mentioned, we will increase our learning rate gradually, but not to a big amount. Okay, and we will try to get into one position where we are saying we are getting attaining some stability. Okay, now from that stage we will continue our training. Like, so yeah, that's why warm-up steps are essential, because uh, if we directly, so I just gave a parameter of 3e minus 5, right? It may happen this is not the correct learning rate. Okay, Now I can transform my learning rate to a more stabilized form, like a stabilized form for my weight update by increasing it slightly. Okay. And getting into a stage where if I start from that state, okay, I will update the weights on a larger scale, but I will get to the minima position very early. So yeah, that's why warm-up sessions are essential. And 20 is still like, this is a hyperparameter. I just gave a 20 as a number, so it's not much special, but it's mostly used by many Kagglers and other research communities also. So yeah, this is something anyone can fine tune, or like anyone can tune to check the performance. So yeah, I'm not sure why this is not happening. I'm just closing this. Yeah, cool. Why you are not happy? Run. Gemma Tokenizer has no attribute pad. Gemma Tokenizer has no attribute pad. This is something which I have not expected. So I have config here. Got Gemma Tokenizer. Yeah, this is it. Okay, let's look at. Let's search actually. I know. Okay. Says my brother, you are providing function as a tokenizer argument. Rather, you should provide tokenizer object. Tokenizer object. Encoder was a tokenizer object. Has. this ran here. Next sleepy actually. Okay, so I got trained yes here, I got bad yes here. I got data collator here. Not sure why it's not taking. It's pretty weird, like if oh that was RAM 16 GB GPU. Cool. So it took me a while to do this. So apparently uh, this pad function was not taken from this tokenizer, so I implemented this two function. So I got this from Stack Overflow. I don't know why it was not working, but yeah, as you can see, like we are training and it will take around 3 hours of time. Okay, maybe I can increase the batch size, but I'm already hitting my GPU memory. So yeah, these are all the things you can do. So yeah, I hope you learned something new in this video, and I'll be uploading more videos regarding this competition in this channel. So just stay tuned to watch more videos in this. So yeah, it's training and it's taking time. Cool.